In the last session, we did a closed loop transfer function of closed loop pulse transfer function of digital control systems. We did some examples. Moving on, we'll start with the analysis now, and the steady state analysis of digital control systems. So, like as you have done in case of analog control systems, you can study the steady state error, you can derive the stability of a system. So there are, you can go for the transient analysis, you can go for the steady state analysis. We are doing the steady state analysis of digital control systems. So in case of Z domain, when you talk about the output, if you have the total transfer function of a closed loop system is Tz, then your output Yz will be equal to Tz into Rz, and the steady state output that's given by Yk as limit k tends to infinity. In case of a Z transform, applying the final value theorem, limit this tends to limit Z tends to 1, Z minus 1, Y of Z. So using the final value theorem, we can find out the output. We can find out the output of the system, the steady state output of a system, and accordingly we can also derive the steady state error for the system. Using this equation, let's say we want to find the steady state output of the following system. Subject to a unit step input. Fine. So the solution of the system, your system is actually this. Tz is equal to 0.36 divided by Z minus 0.457. So you want to find out the steady state output of the system. So limit k tends to infinity, Yk is equal to limit Z tends to 1, Z minus 1, Yz, where Yz will be equal to limit Z tends to 1, Y Z minus 1, Z minus 1, Yz will be equal to Tz into Rz, where Tz is 0.36 divided by Z minus 0.457 into Rz. Rz for a unit step input means Z divided by Z minus 1. Fine. The Z transform of a unit step input is Z divided by Z minus 1. So this means Z minus 1 cancels out. Substitute Z equal to 1. This means 0.36 into 1 divided by 1 minus 0.457. Solve this, you will get 0.663. Fine. So this is the steady state output of the system when subject to a unit step input. So using the final value theorem, you have studied the final value theorem in case of Laplace. Limit t tends to infinity, y of t is equal to limit s tends to 0, s y of s. So actually that's your final value theorem in case of Laplace domain. In case of Z domain, it is limit k tends to infinity yk is equal to limit z tends to 1 z minus 1 y of z. So this is how you find out a steady state output of a system. Now once you know the steady state output of a system, for this case that we have actually done, if the steady state output is 0.663 and the input was a unit step input, that means actually 1. So this means for a unity input, your output is actually 0.663. Now this is actually in discrete domain. I cannot draw a continuous time function. So you can simply state that the steady state error for the system is 1 minus 0.663. That's around 0.37. But instead of doing that, we can go for the steady state error analysis, like we have derived for analog control systems. Using the type of a system, you have type 0, type 1 and type 2 systems for different responses, for a step response, for a ramp, for a parabolic response. So for a closed loop system, you can directly say whether your output has a finite error, whether it has an infinite error, or whether it has a zero error. Fine. So if you have a closed loop system, RS you have a closed loop system whose open loop transfer function is g of s. You have a sampler here of t that puts this equal to e of s. So for this case, we have already seen that Ez will be equal to Rz divided by 1 plus g of z. So the steady state error will be given by the final value theorem again. So E of infinity will be equal to limit, that means actually limit t tends to infinity, E of s will be equal to E of k will be equal to limit z tends to 1 z minus 1 in z domain Ez. Fine. Or in other words, you can say E of infinity is equal to limit z tends to 1 z minus 1. Instead of Ez, I can write Rz divided by 1 plus g of z. So this is my steady state error value. For a step input, this is E of infinity, limit z tends to 1 z minus 1 into Rz divided by 1 plus gz. So for a step input, E of infinity is equal to limit z tends to 1 z minus 1. Instead of Rz, I will write z divided by z minus 1 into 1 divided by 1 plus gz. Fine. So E infinity is limit z tends to 1 z minus 1 Rz divided by 1 plus gz. So as I know, for a step input, Rz will be z divided by z minus 1. So this cancels out. This means E of infinity is equal to, applying the limits, z is becomes 1. This means 1 divided by 1 plus limit z tends to 1 gz. Because I do not know what is the transfer function gz, so I cannot apply the limits here. This term I have already applied the limit to. I have substituted z equal to 1 there, so I am left with this thing. I can put this as 1 divided by 1 plus kp, where kp is what, which we have actually already again done in the analog domain. Kp is equal to limit z tends to 1 g of z. Fine. So E infinity, the steady state error, is equal to 1 divided by 1 plus kp for a discrete control system with kp equal to limit z tends to 1 gz. That we have also done for an analog system. वहाँ पे आपका जो kp था, that came out to be limit s tends to 0 g of s. यहाँ पे आपका kp जो है, this is the position error constant. It comes out to be z limit z tends to 1 g of z. Similarly, for a ramp input, rz is tz divided by z minus 1 square. Therefore, E infinity becomes limit z tends to 1 z minus 1 rz, that's actually tz divided by z minus 1 square into 1 divided by 1 plus gz. Fine. So इस सब का limit है ये. So 1, this cancels out, so you are applying the limits. This will come out to be t divided by limit z tends to 1 z minus 1 into 1 plus gz, which implies t divided by limit z tends to 1 z into 1 plus g, z minus 1 into 1 means z minus 1 plus limit z tends to 1 z minus 1 g of z, which implies t divided by, when you substitute z here it becomes 0, so niche you can say that you are left with z minus 1 gz. So that's actually put to t divided by kp. Fine. So मैं यहीं पे लिख देता हूँ, E of infinity is equal to t divided by kv, where kv is limit z tends to 1 z minus 1 gz. Similarly, you can do for a parabolic input, where kv is known as the velocity error constant. Parabolic input, where rz will be equal to t square z plus 1 divided by z minus 1 cube. And you substitute this, E infinity will be equal to 1 divided by t square divided by ka, where ka will be equal to limit z tends to 1 z minus 1 square gz. Fine. Where k is known as the acceleration error constant. So for different types of system, you have already done the type of system using the as domain. So you define the type of system, say for depending upon the pole, whether it's at the origin or not. For a system which has 0 poles at the origin, that means it is a type 0 system. With the system having 1 pole at the origin, you can say it's a type 1 system. But in case of discrete domain, we define the type of system using this equation. So we actually check out whether the z is located at the if there is any root of z that's actually located, whose magnitude actually corresponds to a unit circle of radius 1. Fine, of a circle of radius 1. So if you have any such system where z minus 1 is equal say for example you get a system where n comes out to be 0, and you will say this is a 0 order system. That means there is actually no pole of z that's actually located at the circumference of the unity circle. If you have n equal to 1, you will say there is one pole that's actually located at the circumference, along the circumference of a unity circle. If n is equal to 2, you will say there are two poles of z that are actually located along the circumference of a unity circle. So for type 0 system, Kp comes out to be constant, where Kp is actually given by limit z tends to 1 gz. So for this system, Kp comes out to be constant, so you can say A infinity is equal to finite, Kv is 0, Ka is 0, so A infinity is infinity, A infinity is infinity. Fine. So you can actually draw that table. It's similar to one you have already drawn for a the one you have actually already drawn for what you can say the continuous time system, analog system. So for a step input, ramp input, and a parabolic input, for this is the value of steady state error. Fine. For a type 0 system, step input is finite, that's actually k divided by kp, 1 plus kp. Fine. Ramp, it comes out to be infinity, this comes out to be infinity. For type 1 step input, error is 0. For type 2 step input, error is 0. For type 1 ramp input, error is finite and it is equal to k divided by kv. This is 0, this is again infinity, and this is k divided by ka. Fine. So for all other input, for all other types 3, the steady state error for all the different types of inputs will be 0. So this is one analysis. We will do a numerical here. So let's do a numerical. For the following system, find Kp, Kv, and Ka. This is your system. S plus 1 divided by S plus 4, S plus 5. We do not need to find out the total transfer function of the system. We only need to find out, we need to solve this and obtain GZ. So once we know the type of GZ, we can actually determine the type of system and find out the values of Kp, Kv, Ka. Right. So G of Z, as we know, when Z zero order hold is in parallel with, in cascade with any transfer function Gp, G of Z will be Z minus 1 by Z, Z transform of Laplace inverse of Gp divided by s, where gp is s plus 1, s plus 4, s plus 5. So that means g of z will be equal to z minus 1 by z transform of Laplace inverse of s plus 1 by s plus 4, s plus 5, doing the partial transfer function. One by 20 s plus 3 by 4 s plus 4 plus minus rather minus 4 by 5 s plus 5. Z minus 1 by z transform of Laplace inverse of 1 by 20s is 1 by 20 plus 3 by 4 e raised power minus 4t minus 4 by 5 e raised power minus 5t. So this becomes z minus 1 by z. 1 by 20 is z by 20 z minus 1 plus 3 by 4 z divided by z minus 0.67 minus 4 by 5 z t here is 0.1 seconds. Fine. So z transform e raised by minus 4t will be z minus e raised by minus 4 capital T. Substitute the value of capital T, you will get z minus 0.067 z divided by z minus 0.61. Fine. So this is your g of z. So we have found out g of z. Now we can say Kp is limit z tends to 1 g of z. So so when you will multiply z minus 1 by z with all these three individual terms, in the first case z and z cancels out, z minus 1 cancels out, so it remains 1 by 20. In every other case you have z minus 1 divided by z minus 0.67. so in every other case z will make the system tend to 0. Only for the first term z minus 1 cancels out, so this 1 by 20 remains there. So Kp is equal to 1 by 20. Kv is equal to limit z tends to 1 z minus 1 g of z. So in this case, when you will substitute even z minus 1 with 1 by 120, so z minus 1 will tend to 0 when you substitute z equal to 1. So this will be 0. Ka similarly 1 by z tends to 1, z minus 1 square g of z will also be equal to 0. So these are your values of Kp, Kv and Ka. Now if you have been given a system with a step input, so you can determine whether this system will have what will be the value of error. Fine. So if you have been given a step input, you can say K by Kp. You can say this is steady state error is around 20. Fine. So this is about the steady state error analysis of discrete control system. So we'll continue with the analysis in the next session.